Okay, so welcome to Monday Fun Day. Just a standard housekeeping on Monday. This is a regular week, so I have office hours tomorrow morning. If anything bothers you, make sure you show up then or shoot me an email. If office hours don't work for you, make sure you shoot me an email. We can meet some other time. There's no wackiness this week, unlike next week where there's like spring break half the week or two-fifths of the week is spring break, which affects us in no way, but I don't know. Anyway, so next week will be confusing. Any concerns about the schedule or anything? All right, so before we pick up where we left off last time, remember we had one problem to do. I did get a question before class that I want to answer, and I want to do it in the most winding and unwieldy way as possible. Okay, so many of you have had me in class before, right? For say Calc 3 or something, right? Calc 1, whatever. And if there's one thing you know about me, it's that even though I'm like kind of old, right? I'm like a cool old guy, right? I'm not like your parents or something, right? Those people don't know anything. They don't know what it's like to be a youth of today. Do they agree with that? Not like me, though. I know what it's like to relate to the youth of today. So if I know anything, it's that young people like two things. They like math, right? Nods, right? I mean, I have cousins that are you people's age, right? And they can't wait to see me at family gatherings, right? You can see it on their face. Finally, I get to talk math with somebody. That's what young people like. The other thing they like is when old people complain about how hard we had it back in our day, right? As a way of showing you people how soft you are, right? Don't young people like that? So back in my day, when I was your age in my introduction to differential equations class, this was a long time ago. It was before TikTok, Snapgrams, things like this, right? I wasn't what you kids like. Candy Crush, right? We weren't playing Candy Crush back in those days. We're playing Halo. You guys play Halo? On the original Xbox. Anyway, in that class, I, of course, did whatever the equivalent of chapter 6 was, right? And this is what we needed for chapter 6, this table right here. I had to memorize this. You know, so on my chapter 6 exam, whatever chapter it was, right, there were Laplace transform questions, and I had to like invert the transform based on this table, but I had to know this. It wasn't given to me. So I guess a natural question for you people is, do you think that you have to memorize that table? No, because people are soft, you know, not like me back how I had it. But no, you're not gonna have to memorize this. Somebody asked me, right? So on your chapter 6 exam, which I guess also has chapter 4 on it, whatever the next exam is, you'll just be given this table, be stapled to the back, right? So you shouldn't worry about memorizing it. What you should worry about is like, what is it telling you, right? So if I have this table, can I use it, you know? So that's what you should focus on throughout this chapter. Okay, so where we left off last time was this problem here. Okay, so we solved the initial value problem using the Laplace transform, and we broke it down by steps. It was very warm in here, so I may have been asleep while we were doing this, but I vaguely remember doing this and also sweating a lot. And then we stopped because we were mostly out of time. So what I want you guys to do is do this problem using the exact same steps. So transform both sides, isolate the L of y, see if you can use the table to go backwards. So let's take maybe 10 or 15 minutes to try that. I'll go around and talk to you while you're doing it. Just see if you can follow the exact same steps from above. I guess just as a reminder, right, in case you forgot over the weekend, you do want to start by Laplaceing both sides, right? Would I agree with that? So start by Laplaceing and then see if you can regenerate this step, right? Laplace both sides though. Last time I had a 0 on the right-hand side. Laplace of 0 was 0. That's not the case now, right? Right-hand side is not 0. I don't have a good way of having this up on the screen and also the table, right? But you guys can access the table. I want to make sure you know. I want to make sure you're here. So also left. Yeah, so well, this is almost. Okay, so it's been 10 minutes or so let's just stare at the board and see if you guys agree with the steps so far. See if I can get the silly glare off of this. Sort of. Okay, so following the steps of the previous problem, was everybody able to arrive at this? Is there any confusion here? Okay. Okay, so I guess I should have reminded you at the beginning. This takes getting used to, of course, right? So the first like 3 or 4 times you do it, I know it's kind of a mess, right? You gotta get used to it. But anyway, once you sort of get used to the flow is always the same. I'm going to Laplace both sides. Laplacing the left-hand side usually means I got to run back to that theorem that tells me how to Laplace a y double prime or a y prime. There is no y prime this time, right? But you got to scurry back to the theorem and be like, oh yeah, that's what L y double prime is. You notice I get tired of writing the script DL, right? You can do whichever you want. And Laplace on the right-hand side is usually just a matter of scurrying to the table, right? You agree with that? So you could feed sine 2t into that formula from last time, but there's no reason to get the table. And then you sort of simplify, right? You're like, again, y of 0 over 0, y prime 1, so on, right? So you just plug in, and then your goal is to isolate L of y. So let me isolate L of y. And then we're actually sort of almost done, but we're almost done up to the, you gotta be comfortable using the table. Okay, so L of y is like this. 2 over s squared plus 4, s squared plus 9, plus 1 over s squared plus 9. And it's actually kind of important that you think of it that way. I mean, because if you're going to use the table, having the terms separated like this is useful. Like if you want to have those terms together, like this. Well, actually, I'm not even going to write it, but if you try to combine these two fractions, you've made the problem harder on yourself, actually. You know, more things sort of separated so you can deal with things term by term. So speaking of things term by term, now you look at both terms and be like, can either of these be inverted from the table right now? Let me bring the table up. One of them is pretty close, right? Can you handle this one from the table? This one, yeah, this term. If I just give you this, nothing else, can you handle this? What is this? How do you handle it?
You take the 1 and the numerator of 3, just so it fits into the sign of 18.
Yeah, you're looking at line 7, right?
But then you multiply it by 1/3.
Yeah, right. But you can't just like erase, 1, put a 3 there. You got to compensate, right? So this now, sort of a check, and this becomes, as Cody says, right? This is like a sine of 3t. Is that right?
So multiply by 1/3.
Oh, sorry, lost my third. Is everybody okay with that? So we know the part of our answer is a sine 3t over 3. Now, of course, this other part we haven't dealt with yet, right? We got to deal with this. And the table is not immediately helpful, So any ideas how to handle this? Maybe the previous example we did on Friday is helpful here. So here's step 3 from last time, right? Step 3 from last time, we arrived at something that looks kind of similar. We had a fraction we were trying to invert. What do we do with that fraction? Yeah, so anytime you have a denominator that can be factored, and this is factored, right? Term times term, right? That's just screaming at you to please scurry off to Wolfram and ask it for the partial fractions decomposition. Because what that does is it takes some of this and breaks it into pieces where this will be one denominator, then that'll be a separate denominator, That's what partial fractions does for you. So I'm going to do that. I'm going to scurry off to Wolfram and ask it. Let's see, I should share my screen. Hey, should anybody do it? No? Okay. So partial fractions. You got to handle the entire fraction. S to the second plus 4. S to the second plus 9. And it breaks that real nice for us. we get here, it equals 2/5, and maybe I should keep that 2 with it, right? So 1/5 twice s squared plus 4, and then minus, here I am going to peel off the 2/5 times 1 over s squared plus 9, and I'll keep this going here at 1/3, 3 over s squared plus 9, like that. And now I'm basically done. I'm running out of room on the board, but let me go back to the handout. Stop. Not the handout, the table. Okay, move page row here. Okay, now, is this friendly? It is, right? Is this friendly? Almost, right? How do you make this friendly?
You do the same thing as the last one we did.
Yeah, 3, compensate with dividing by 3 outside, right? And now, you sort of scan yours across and you're like, I like that, like that, like that. Now we're done. So now we say, okay, we were looking for y, weren't we? With that original goal a long time ago, right? We're looking for y. We learned that the Laplace of y was all this stuff, right? So now we can say, well, y is 1/5 sine of 2t minus 2/15 sine of 3t plus 1/3 sine of 3t. So you can leave it like that if you want to, or you can combine the sine of 3t's if you want to. It doesn't matter. So we had a bunch of S stuff, and we finally translated back to T stuff. So again, this is how all these problems go, and they take getting used to. In particular, this stuff over here might take more work than this. I don't know, right? You can certainly imagine more complicated things over here. In practice, like in your homework on an exam or something, it can't get much more complicated than this, or you're just like killing a bunch of time, you know. But this is always the flow. Transform. Isolate L of y. Once L of y is isolated, now it's like algebraic manipulation trickery time. Get a table match, you know, or a series of table matches. Okay, so let me pause here and ask. Questions, confusions, annoyances? Do you understand the individual steps here? Do you feel like it's mimicable? Okay. So the last thing I'll say real quick is that problem we were doing, this one. We just did this. Tell me a story here. I like stories, you know. What's the story behind this initial value problem? If we're back in chapter 3. So I'm not asking how you solve it. You could do it that way, right? I'm just asking what, like, where would that have even come from if we're back in chapter 3? What's that modeling for you? Yeah, string mass system or circuit, depending on what story you want to tell, right? What's happening in this particular string mass system? Yeah, so the initial displacement is nothing. It's sitting in equilibrium, right? You shove it, right? 1 meter per second or something, you know? That's true. What does this mean here? I mean, you're right, but what precise, like, where would that have come from, physically speaking? Yeah, so it's like a motor or something, right? There's an external force that's feeding in a sine 2t force, right? Each second, that's how many newtons are being fed in. And the mass is 1 and the spring constant is 9, right? Are you okay with that? Okay, so let's ask ourselves, that solution over there, does that make sense in this context? Is that what we'd expect the string mass system to do? mean, hopefully, all right, because it's correct. Where are the decaying exponentials? Why aren't they there? Why is there no e to the negative 7t or something there? Physically speaking, why wouldn't you expect such a thing? There's no damping or no resistance, however you want to say it, right? Everybody see that? So yeah, in the end, right, you're going to feed in sine 2t, motion's not going to die down, and you're going to end up seeing things that are trying to be sort of in sync with that, right? So we got our sine 2t there, then we're slightly out of phase with that sine 3t because of the initial shove we gave it, you know, and because the spring constant is what it is, things like that. But anyway, that solution on the board, we could have gotten back in chapter 3 for this problem, right? And we could have done it without all this stuff with S's, right? Everybody see that? So I'll say Laplace transform can do what we did before, right? But now it can do a lot more. That's what we're going to start seeing today. Okay. So any questions or comments on this example before we leave it? Yeah. Yeah, so what if, the question is, what if you have a y triple prime, y quadruple prime, whatever, right? Will this tool still work? And the answer is yeah, because there's like this, all you need is a way of transforming derivatives, you know? If you can understand what the nth derivatives transform is, you can do it. And we're not going to use this because it doesn't really come up for us for spring mass systems or circuits. Like we stick with the acceleration ones. But anyway, there is a general formula. So yeah, it just like, it can handle anything from chapters 3 or 4, you know, and a lot more. Again, the spring mass systems and circuits we studied were our second order, so we're not going to use this formula here, but it does exist. Okay, so we won't have time to finish it today probably because we spent a lot of time on this, which is fine, but we are going to start section 6.3 today, which hints at why you care about the Laplace transform. Like, what can it do for you that the characteristic equation stuff couldn't from chapter 3? Why would you care about this tool when we can already do so much, you know? So anyway, today we're not going to do any Laplace transform problems per se. We're not going to do a full initial value problem. We're going to set up some vocabulary and notation that's of use next time when we will broaden the kind of spring mass systems we can study. Yeah. Oh, you're just stretching. Okay. Okay. So the main definition today is called a Heaviside function, and it's the way we're going to model switch flipping of a motor. You want to switch a motor on, switch it off. You're going to model that kind of thing with these Heaviside functions. Okay. So for every real number, there's a Heaviside function defined like this. So U sub C of t is defined like this. It's either outputting a 0 or a 1. It outputs a 0 when time is less than c. It outputs a 1 if time is bigger or equal to c. So first question is, can you visualize that? If I actually graph that, what does the graph look like? Okay, sorry, what did you say again? Okay, so certainly it's just like piecewise line, right? Either outputting 0 or 1. And Riley, you said something? Sorry. Pretty good. Okay, so you look like, let me just draw what Riley said here. So here's time c. That's when you flip the switch. So at time c, suddenly now you're outputting force of size 1, and you keep that force on forever. So this function is either 0, 1, right there. Flip the switch. That's what a Heaviside function looks like. So it's worth pointing out, these things are not continuous, right? However, they look pretty tame, to me anyway, right? Like this is way less exotic than the sine, right? Or tangent or whatever, I don't know. However, chapter 3 can't deal with these, actually. It's not continuous. Everybody see that? So, I don't know. Just to deal with that function on its own, like if you want to shoot in 1 Newton starting here, chapter 3 can't help, but the Laplace transform can't help. We'll see next time. Okay, so that's what UC looks like in general. So what about 2 plus U3? What would that look like? Here's U3. 2 plus that look like? Yeah, good, right? So like any graph transformation, right? You add something to it, just up 2. So it looks like this. Still 3, right? Now, it looks like this. So 2 plus U3, that would be something like this. You're shooting in 2 newtons for a while, and then you decide to flip a switch, and now 3 newtons. You know? That 3 newtons lasts forever. So that's what 2 plus U3 would model. What about twice U4? So not addition this time, but scaling. I mean, just say what that would look like. Well, so the original, like U4, let me draw U4. Like this. Flat. This is what U4 looks like. Now you're going to multiply all the y coordinates by 2. So if you do that, what happens to this line here? Stays where it is, right? Multiply 0 by 2, stays where it is. What if you multiply these y coordinates by 2? Say again, sorry? But all these guys have y coordinate 1, right? So if you just move all the way down the line, multiply by 2, what happens? Yeah, it's just going to be like this. So here's what twice U4 looks like. So all that to say, if you want to model shooting in not 1 newton all of a sudden, right? 2 newtons all of a sudden, or 3 newtons, whatever, right? All you got to do is scale one of these guys by a constant. So 5 U4, what would that mean? At time 4, suddenly you're shooting in 5 newtons. Right? Switch. And again, like this paint graph on the board is not particularly exotic, but chapter 3 shrugs at it. Says, I don't know, man. I don't know what you want me to do with that. Floss can handle these things pretty easily, though, as we'll see next time. Okay, now the glare is terrible. I can't read. U1 minus U5. Think about that. What would that graph look like? Let's think about maybe before graphing, let's think about what this should model. Okay. So U1 looks like this. So with 0, when t is less than 1, but suddenly at time 1 you flip a switch, right? In comes the newton, right? U5, 0 for a while, and then suddenly at time 5, you shoot in a newton, right? Do you agree with that? So let's think about the difference. Okay. Before time 1, what is this difference doing? Nothing, right? 0 there, 0 there, right? Between times 1 and times 5. Between times 1 and times 5. What is that difference doing? Outputting 1, right? Because this is shooting in 1. This hasn't turned on yet, right? Do you see that? Okay. After time 5, what is that difference doing? Yeah, now it's 1 minus 1, right? Now this is shooting in, this is being canceled out. Now you see that? Now this, I think, looks pretty familiar from things we tried to set up in chapter 3, but then we sort of shrugged our shoulders at, okay? What's happening here? No force being shot in for the first second. But then between times 1 and 5, you shoot a force inside the 1 newton, right? But then you turn that motor off. Now it's 0 all of a sudden. Can we see that? So a U sub whatever can be like a switch flip on, and then a minus U sub whatever can be a switch off. Can we see that? This U sub 5, because it was minus, it turned off this U1. Some of the motor's off. You want to graph it. 0, and then it's 1, turn the thing on, keep it on for a while, and then times 5, we turn it off. You okay with that? Okay, so given that, we now have like language to talk about functions that look like this, you know, UCs. You can scale UCs, you can add them, subtract them, whatever. But whatever you're doing, you can sort of describe a graph like this. So anyway, so this is U1 minus U5. Let's What does that say? What if you slap a 5 on there? Scale everything by 5. How's that behave? Yeah, multiply the output by 5. Like that. Right? Now instead of shooting in 1 newton, you're shooting in 5 newton. Right, see that? Okay, so these are really nice because I know there's one more question on here, but I want to just give you one of these things. Total here. Like with a lot of notation, right? They take a ton of English and condense it down. There's so many things you don't want to say in English all the time, right? That's why mathematical notation exists. So I'm going to write down a combination of these functions, and you tell me the English story here. Okay, so what kind of force does this represent? Let me write down. There's a lot of English to explain what's happening with that function, right? So I'm going to tell you, this is an external force being applied to a circuit or to a spring mass system. Describe how that force is behaving. If I cover this up, what's happening? From 1 to 3, you flip the switch, right? And how much force is being shot in the system? 2. 2, right? Oh, but then you flip it off at 3, right? Let's go. What happens next? Yeah, 4 to 8, but now I've decided to shoot in 7 newtons, right? More force, right? So on at 4, off at 8, and then what happens next? Turn on at 9, turn off at 13. How much force is being shot in now?
Oscillate.
Oscillating, right? You can slap whatever you want here, right? And this little difference, if you scale it, right? This little difference just says whatever's right here, on there, off there. Did I say this? The ton of English packed into this, right? But if you write it like this, as long as you know what the Laplace of like U1 is, or the Laplace of like sine t U9, whatever, right? As long as you know something like that, you can plug this into a Laplace transform problem, and the Laplace can handle it. Whereas again, back in chapter 3, there's nothing to be done here. Chapter 3. We shrug, we back away slowly, right? But Laplace is not afraid of something like that. Laplace says, whatever, you know, we can handle that just fine. Okay, so that's what section 6.3 is about, just giving language to these sort of little discontinuities, so like on-off switch sort of functions. Okay, so let's just say it out loud. What kind of external force is this? What's happening here? Yeah. So at pi, you turn on a motor, right? Sine in there. Then you turn off that motor at 4 pi. Okay. So again, this is actually the key notation for this chapter. Without this notation, the chapter doesn't work. So let me just pause here and ask, if I give you something like what's on the board there, you know, something like this, can you read what's happening in terms of a force or a voltage, if you like that better, you know? If you like a voltage story better, like this one here is saying at time 1, you attach a battery that shoots in 1 volt, right? At time 5, you detach the battery. You can tell a story like that. Attach a battery that shoots in 5 volts and then detach that battery at time 5. I don't know what story you like better, but okay. So with all that in mind of keeping these, of reading these things as external forcing functions, I want you guys to think about these 3 questions. So don't set up the entire initial value problem, but just think about what will go on the right-hand side of the DE. So use the notation from the previous page to write down a formula for the external force. So what you need to be writing down are things like this, you know. So use that notation to write down what these external forcing functions are. Take 5 minutes to go. Are you guys ready to talk about these? All right, so talking to most of you, it seems like 7 and 8 were okay. 7 was like this. You wrote down something like this, 5. This is actually on the previous page. Like this. That's what the forcing function is. And again, notice how compact this is, right? You can slot that right into a DE. This one, A is not quite so compact, but how do you write that down using notation like this? What do you guys think about that? So the same thing as 7, but now there's like another switch you flip, right? So turn it off time 8, turn it off time 13. Okay. 9. How do you do that? So now the forces aren't constant, but same idea. How do you handle that force of sine and that force of t minus 4 at separate times?
Sine of t times u of 0 plus t minus 4 times u of 20 to u of 30, or minus u of 30.
Are you okay with that? So again, when you do a difference like this, you're saying on from time 0 to 10, what's on? Sine t is on, right? On from 20 to 30, what's on? T minus 4. Okay. Okay. So like I said, we're not going to have time to finish the section today because we started with that other example, but we are going to finish today by talking about how you slot these things into Laplace problems. So if you're going to have this inside of a DE and you want to use a Laplace transform, then you have to know how to transform it. Would I agree with that? Because the Laplace transform problem starts by transforming everything. So if you don't know how to transform that, then it's of no use, you know? So we're going to finish today by looking at how you transform those things. And we'll talk next time about how you untransform things, because you always got to go back. So here's the theorem for transforming these step functions. So the Laplace transform of u sub c, you can ask Wolfram if you want to write, but it turns out it's just this. It's a decaying exponential, e to the negative cs over s. So notice the c here. Oops. Always forget to share. The C here, right, matches that C right there, right? Okay with that? And then more generally, if you have Laplace of a function times a UC, like we have with this t minus 4 or whatever, right? This is a little complicated, but it's not going to come very much. But basically, as long as u sub c and this f function are in sync with each other. So this UC function only turns on at time C. This function here has been shifted to the right by C. So they kind of sync up. So this won't come up much, but it is a more general formula. Then you transform that like this. So you handle the UC with the decaying exponential, and then you just transform little f to big F. So I'm going to show you that with a couple examples here. This is kind of abstract here, right? It's hard to read that. So I'll show you with 2 examples down here. Okay, so that's how we're going to end today. So let's walk through these questions and think about what kind of force is happening here. So this is saying at time 5, I turn on a force of 1 Newton, right? And I just leave that thing on. There's no turn off here, right? Agree with that? So let's think about Laplacing that, okay? How do you Laplace that? Say again, sorry? Yeah, good, right? So something like that, it's just this first little formula here, right? So let's just start gathering them. With reported pager out of the way, there we go. Part A. Regardless of put the 5 in for C. So there's the S version of that T function, right? U5 is a function of T. The transform will make it that function of S. Okay, what about U1 minus U7? If you have to transform that, what do you think?
E to the negative s over s minus e to the negative 7 S over S.
Yeah, so transforms work just fine with sums and differences, right? So you can just transform the first minus transform the second. That's what Jacob did. Should be okay with that? Okay. How do you handle C?
Just leave the 10 multiplier out and still do this.
Yeah, good. So a Laplace transform is an integral. Integrals work just fine with coefficients, you know. Coefficients just hang out. So yeah, it's just as Cody said. So you do 10, you negative 2s over s, minus 10, and negative 6s over s, like that. Okay, so if you're in the middle of a Laplace transform problem, and somebody's like, hey, my external force, time 2 I shoot in 10, then time 6 I turn it off. Here's the T version of that force. Sorry, the S version of that T force. Questions or comments on these? Okay. Okay, so these last couple, again, it's not going to be used like this in the homework very much. What really matters is the next time when we invert. But for now, let's practice with this. UC times something. Okay, so let's think about a D. So I have, what is that, U2 times this function. Okay, so notice I have like a sink up here. You see that? So I'm flipping a switch at time 2, and what function comes online? What function comes online is basically t, this right here. This is like the function t, except what have you done? You've replaced a t with a t minus 2. Everybody see that? Right? I mean, you can think of this t minus 2 as this function, but t replaced by t minus 2. Whenever you replace a t with t minus 2, you know graphically what effect that has? Yeah, it's a horizontal shift is all. It's a rightward shove. So this is something like you would have done a lot in algebra 2 or something, right? Your professor or teacher go, hey, your sine t, your sine of like t minus pi over 4, you know? What's the relationship? And algebra 2 versions of you would say, oh, this graph and this graph are the same shape. I just took this and shoved it to the right by that amount, you know? You're just literally taking your hand and like shoving it. And this tells you how much. So anyway, that theorem above works well with functions like this that have been shoved by the same amount as like the switch timer, you know? This time 2, this has been shoved by 2. So when you have a sync up like that, that formula kicks in. So what you now have to do is transform this U2 t minus 2 like that. You have to think about what function got shoved here. And the function that got shoved was t. So what you're going to do is you're going to write down e to the negative 2s. But then that theorem says I have to know how to transform this. Right, because it says that capital F, that's the transform of this little function that got shoved. So if you shove t, now you got to transform t. You don't, by the way, transform t minus 2, right? This function has this like shift baked in. This will sync up here. So anyway, to finish this off, right here, what you have to put is transform t. How do you do that? How do you know that? Yeah, you go to the table, right? So I don't remember what it is off the top of my head. Somebody else can tell me, or we can look it up. But right here, you go to the table and ask the table, hey, t, what's that?
S squared.
E to the negative 2s times 1 over s squared. That's how you transform this.
Why would the e to the negative 2s be divided by s?
No, actually it doesn't. So the theorem, there's no typo there. There's no over s there. Yeah, it's sort of counterintuitive, but, well, I mean, I can tell you why. Like, okay, so the loss of UC of t, you can think of that as UC times 1, right? What's the Laplace transform of 1? It's actually 1 over s, if you look at the table. So that's why you get a 1 over s. Like basically, that theorem is a generalization of this, where just instead of having a constant 1, you have whatever some sort of thing synced up with. Yeah. So it doesn't look right, but it actually is right. Okay, so let's finish off with today by doing that last example. What is that? U pi. So at time pi, you're going to turn on function. What function are you going to turn on? Basically a sine, right? Well, you shove the sine to sync up with that pi. So again, you get a little match. So basically, you're turning on, again, you're turning on the sine curve, but you're waiting to turn it on until pi when this little switch flips. Okay, so again, this use of C thing, I handle by just doing a decaying exponential, C replaced with pi. Then how do I handle this piece? Go to the table and you transform sine, right? So where's that? Yeah, so even though I was forced to memorize this 15 years ago, I of course don't remember it now. Right? So I also scurried to the table. Okay, so what's missing for us now to sort of slot these into initial value problems is what we'll start with next time. So next time it's like, okay, suppose you're staring at one of the S things. How do you go back, right? This is a forward translation. How would you do a backwards translation? So that's how we'll start next time. And then hopefully we'll have time to fully connect this back to chapter 3 by the end of Wednesday.
So will this change the
Oh yeah, that's a good question. Yeah, probably does. Let me just send an email about that. Yeah. So I'll send an email and I'll just say any of the reversing, right? We'll just wait on. Everybody okay with that? Okay. All right. So I'll see you guys on Wednesday.